You know, for pretty much all of human history, we've just accepted aging as a fact of life. It's undeniable, right? We're born, we live, and then our bodies start to break down. But what if that's just not true? What if aging isn't some unchangeable law of the universe, but a process we can actually understand and maybe, just maybe, do something about?
Woody Allen really hit on something there, didn't he? It's a feeling we all get, this deep curiosity about why our time here is limited. And for centuries, that exact question has been one of the biggest puzzles for the greatest minds in science.
See, the real question isn't just how do we live longer? It's about getting to the why. Why do our cells, the very things we're made of, seem to have a built-in expiration date? And when you start asking why, you change everything. Aging stops being this scary, inevitable thing and becomes a biological problem. And problems, well, problems can have solutions. So, to really get the massive breakthrough we're going to talk about, we first have to understand the old ideas. And honestly, the best way to think about it is that old story of the blind men and the elephant. You know, the one where each man touches a different part of the animal and comes up with a completely different idea of what an elephant is. So you had one group of scientists who felt the elephant's sturdy leg and said, aha, it's a column. That was the wear and tear theory, the idea that our bodies just get worn out like an old car. Then another group felt the tusk and said, nope, it's a pipe. That was a hormonal theory, blaming everything on our hormones declining. And look, they were both touching on something real, but they weren't seeing the whole picture. And it didn't stop there. Another group felt the wiggling trunk and decided the elephant was obviously a snake. That became the free radical theory. Then a fourth group felt its broad side and insisted it was a wall. That was the genetic theory, the idea that we have aging genes that are just programmed to fail. And that right there was the huge problem. Each and every one of these theories was based on real data. Our bodies do wear out, our hormones do decline, and free radicals do cause damage. But none of them could explain the one thing that connected it all. They were just describing symptoms, not the root cause. They couldn't see the entire elephant. So what changed? What was the big aha moment that finally let scientists step back and see the whole animal? Well, it all started with a discovery that completely flipped our understanding of cells on its head. Okay, so for a long time, there was this myth based on a famous experiment that our cells could live forever. But then, in the 1960s, a scientist named Leonard Hayflick noticed something fishy. It turned out the original experiment had a huge flaw. They were accidentally adding new cells to the dish every day. Hayflick proved that normal, healthy cells aren't immortal at all. In fact, they can only divide a certain number of times before they just stop. It's called the Hayflick limit.
And get this, what Hayflick and other researchers started to notice was just wild. A mouse, with a lifespan of about 3 years, its cells can divide maybe 15 times. Us humans, we get about 40 to 60 divisions. But a Galapagos turtle, which can live to be 200, its cells can divide around 110 times. For the very first time, we had a real clue. The clock of aging was literally ticking inside ourselves. The only question was, what was that clock?
The answer turned out to be these little things called telomeres. You've probably heard the classic analogy. They're like the little plastic tips on your shoelaces, the aglets, that stop the whole thing from fraying. And every single time a cell divides, a tiny little piece of that telomere gets lost. The shoelace gets a little bit shorter.
Okay, but here's where it gets really interesting. That whole shoelace thing, well, it's wrong. Or at least it's a massive oversimplification. Your DNA doesn't just unravel when the telomere gets too short. The real process is way more subtle and, honestly, way more incredible.
The real key to the whole puzzle is this amazing enzyme called Telomerase. Think of it like a maintenance crew for your DNA. Telomerase has this incredible ability to go in and add back those lost bits, re-lengthening the telomere. It basically resets the aging clock in a cell, which is why our stem cells and, unfortunately, cancer cells can keep on dividing.
Okay, so here's how it really works, step by step. As your telomeres get shorter, it's not like your DNA explodes. Instead, it changes how your genes are read. Think of your DNA as an orchestra, and the telomeres are part of the musical score.
As the score gets shorter and tattered, the music just gets worse and worse. The cell can't repair itself as well, damage builds up, and that slow decline in function, that is what we actually experience as aging. So look, this isn't just some abstract science lesson. Getting this right is the key to understanding and maybe one day treating the diseases that we all worry about. There's this fantastic analogy from Dr. Michael Fossel. Imagine your genetic risks, for things like heart disease or Alzheimer's, are like big, sharp rocks at the bottom of a lake. When you're young, your telomeres are long, so the water level is high. You sail right over those rocks, no problem. But as you age, the telomeres shorten, the water level drops, and suddenly, those rocks you never even knew were there become a very real danger. Now, we've got to bust a really common myth here. Getting one single measurement of your telomere length doesn't really tell you that much. I mean, mice have way longer telomeres than we do, but they live much shorter lives. What really matters isn't how long they are at any one moment, but the rate at which they're shortening over time. That's the real health indicator.
And here's another mind-bending part of the puzzle. You might think, okay, but my brain cells don't divide, so this doesn't affect them. But the support cells all around them, like the microglia, they do divide. And as they get old and stop working well, they can't do their job of supporting the neurons. So the neurons become these innocent bystanders that get damaged because their support system failed.
And this one idea, this indirect aging, it's the hidden thread that connects so many of our worst diseases. For heart disease, it's the aging cells in our arteries. For Alzheimer's, it's those aging support cells in the brain. For osteoarthritis, it's aging cartilage cells. It all comes back to the health of these dividing support cells. So where does this all lead? Well, this isn't just about explaining the past. It's about creating a roadmap for the future. We're talking about a complete shift in medicine, away from treating one disease at a time and toward treating the root cause of them all, aging itself. And this quote from Dr. Fossel just says it all. This isn't an academic exercise. For scientists, for doctors, for all of us, the real goal is to be able to treat the aging process so we can prevent and even cure the diseases that cause so much pain. So how do we actually do it? Well, researchers are basically chasing three big ideas right now. First, finding things that can switch our own telomerase genes back on. Second, a more direct approach called gene therapy, using a safe virus to just deliver the telomerase gene right to our cells. And third, a newer idea using that mRNA tech you've heard about to give ourselves temporary instructions to make telomerase. But let's be absolutely crystal clear on one thing. This is not about tacking on 50 more years in a nursing home. That's not the goal. The only way you can dramatically extend someone's life is by extending their health span, the number of years they live in good health without all the chronic diseases we associate with old age. I know, it sounds like something straight out of a sci-fi movie, but a lot of top researchers in this field genuinely believe that by resetting our telomeres, a healthy human lifespan of 200 years is possible. This isn't about living forever, it's about adding decades of healthy, active life. So I'm going to leave you with this question. If you had twice as much healthy time on this planet, what would you do with it? What would you learn? What would you create? Who would you become? The amazing thing is, this isn't a fantasy anymore. It's a real scientific revolution, and it's happening right now, one cell at a time.